guys. Welcome to class for today for Friday. This fortunately will be the last day, I believe, that we'll have to start the semester with a video. While we won't have class on Monday for Martin Luther King Day, and we don't have class on Tuesday because we never have class on Tuesdays, we'll be back in swing on Wednesday, and I expect to be back at campus to actually meet all of you in person and proceed with class without having to use these videos to do so. Just a reminder, as sort of we work our way through the week, homework, which posted to WebAssign yesterday, and well, normally Thursday assignments would be due on Sunday. The homework from this Thursday will be due next Sunday at 9:59 p.m. Next Sunday, just since it's the first week, give you guys an opportunity to get your WebAssign access code sorted out. You might actually be able to sign up on WebAssign without an access code temporarily, but ultimately know that you're going to need an access code in some sense as soon as possible to give yourself access to all the homework assignments. So homework, which posted yesterday to WebAssign, due Sunday, 9:59. All right, so what are we going to work on today? We're going to continue with, in some sense, this sort of basic, essential skill building, but no, the more ironclad you have this stuff in your brain, the better off you're going to be here moving forward. So, in particular though, we're in section 1-2, which is on radicals and exponents. So these two concepts, well, seemingly distinct whenever you first see them, have some amount of familiarity with each other to where we'll see actually as we go through the class today how these two things are actually sort of two sides of the same coin in some sense. So let's sort of just head right into it though. So let's start talking about radicals. So what is a radical? So first, let's just give notation for radicals. Okay, so notation for radicals. You're going to see a number inside a symbol such as this with another tiny number on the outside. What does this mean? This is the number that multiplied times itself n times is x. This is the number that multiplied times itself n times is x. So the little n tells you how many times the number you're looking for has to be multiplied by itself. The x tells you what number you have to multiply to. So, examples? Things you've probably seen before, but good to remind ourselves of what exactly these things mean. So what about 3 radical 27? This is 27, well, we're looking for a number which multiplies by itself 3 times to be 27. So in effect, we're looking to solve this problem. What number times itself 3 times is 27? The answer, 3. Note, if you looked at the third root of minus 27, I used the word root there, it is actually like sort of synonymous, the word radical and root. So here if we have the third root of minus 27, this is saying what number times itself 3 times is minus 27. And of course, you know that if something is going to multiply to be negative, it's got to be negative itself. And in particular, if you have 3 things multiplying to be negative, it's got to be, well, in this case, multiplied to be negative 27, it's got to be negative 3. Because, well, for 3 things to multiply to be negative, the thing being multiplied has to be negative. If the thing being multiplied is positive, you end up with something positive. Also, just a note, so let's observe this, that if n is omitted, it is assumed n is 2. So sometimes you won't see the n written. So here, in both of these examples that we gave, the number the number of times we need to multiply that thing by itself is 3. If you happen to have the n omitted, we assume that it's 2. So if we have something like this, 16 with no number written here, it's assumed that even though that number isn't written, that number is a 2. So in other words, to answer this problem, you have to ask yourself what number times itself twice is 16. Now, if you want to answer this question, you can notice there's actually two numbers which would express this, because 4 times 4 is 16, but just as well minus 4 times minus 4 is 16. Since we have the number multiplied by itself an even number of times, whether you put in a positive or you put in a negative, you'd end up with 16. So we put our foot down to give ourselves a single result to the expression. And if you ever have the option of a positive or a negative, when you're dealing with, like in this case, a square root, a second root, you put your foot down and say that it's going to be positive. So rather than us saying this to be negative 4, we're going to say this to be positive 4. So to make a remark about that, when dealing with even roots, the result is positive when evaluating an exponent, when evaluating a radical. So, just as well, if we had, say, the fourth root of 16. Well, here we're looking for a number which multiplied by itself 4 times is 16. And what number multiplied by itself 4 times is 16? Well, it could be 2, or it could be minus 2. Which do we pick? Well, when dealing with our even roots, we put our foot down and say we're going to get the positive thing back in return. So we're going to say the answer is 2. In some sense, you could equally validly put a minus 2. But if you wanted the negative, you'd have to put a negative in front to denote that. Now, something to observe about this. If I put the minus sign out in front of the fourth root, I simply get the negative result. What if I tried to put the minus sign on the inside? Note, what if we were trying to figure out the number which multiplied by itself 4 times is minus 16? Well, the problem is, if you're trying to find the number which this is on a number line, you're not going to find it. Because if you use a positive number, well, no positive number times itself 4 times is going to be negative, but at the same time, no negative number times itself 4 times is going to be negative. Because negative times negative is positive, negative times negative is positive, positive times positive would be positive. So interestingly, when we have the negative inside and an even number of numbers being multiplied to become that thing, this has no solution on the number line. Now, there are numbers out there which could solve this or could be the result of this, and you have to invoke imaginary numbers to do so. We're really not going to deal with that in this class. And in fact, calculus doesn't even traditionally involve that until you get to like the 400 level. But yeah, ultimately, to say this more generally, even roots with negative numbers inside have no solution on the number line. Another example of this, just to give our mind's eye yet another sort of a thought here. What if you had square root minus 9? This is a number. Now remember, first off, there's no number written here, like no n written here outside the root. And when there's no n outside the root, we assume that it's 2. So here, in particular, we're looking for a number which times itself would be negative 9. There's going to be no solution to this. Because If you took a positive times a positive, you get a positive. If you took a negative times a negative, you get a negative, or excuse me, a positive. So no number, positive or negative, would multiply by itself to give you minus 9. This guy's got no solution. Anytime you have an even number of numbers multiplying, it could possibly be a negative if you're using a number off the number line. But in general, when you're dealing with radicals, the little number outside the root symbol is telling you how many times you have to multiply, and then you just need to find the thing which multiplies a certain number of times to be whatever is inside. So, like in the case, what thing times itself 3 times is minus 27, that thing came out to be minus 3. Okay, so with this being said, we sort of have a notion now of what radicals are. Let's step into the world of exponents. And then ultimately we'll tie these two things together. So when it comes to exponents, let's sort of start dealing with this. Well, exponents, let's just say what they are. Repeated multiplication. That's what exponents are. Think about this. To build this up, let's say 2 plus 2 plus 2 plus 2. Repeated addition is what I could call this, because, well, we're taking 2 and just adding it repeatedly. You know that could be expressed as multiplication. Repeated addition is multiplication. Well, what about repeated multiplication? As we've said above, repeated multiplication is exponentiation. Well, I guess technically above we said exponents are repeated multiplication, but the noun form of, or well, maybe it's the adjective, whatever it is, repeated multiplication is exponentiation. How would we express 2 times 2 times 2 times 2? We write this as 2 with a little 4 above it. The little 4 denoting that you're going to take that 2 and multiply it by itself a total of 4 times. Which in this case, 2 times 2 times 2 times 2, times 2 is 4, 2 again is 8, times 2 again is 16. Repeated addition, multiplication, repeated multiplication, exponentiation. Now, from this, we can start to sort of, I guess, familiarize ourselves maybe with what exponentiation is. So let's sort of walk through this. So let's think about what like 3 to the 1 is. 3 to the 1 is 3 times itself once. 3. What about 3 to the 2? This is 3 times itself twice. 9. 3 times itself 3 times? 27. 3 times 3 times 3. 3 times itself 4 times. Well, 3 times itself 4 times, 3 times 3 times 3 times 3 is technically 9 times 9, which is 81. Another way to think about this is that 3 times itself 4 times is just 3 times itself 3 times. It's a mouthful to say, but it's true, right? 3 times itself 3 times another 3 is 3 times itself 4 times. Another way of thinking about this is that if you know what 3 to the 4th is, you can get to 3 to the 3rd by dividing away a 3. You know division is just the inverse operation. It undoes multiplication. So if you know what 3 times itself 4 times is, you know what 3 times itself 3 times is by division. Let's note that this pattern continues. Divide by 3 again. Now you have 3 times itself only twice. Divide by 3 again. Now you have 3 times itself only once. But what can we do at this point? Let's take it one step further. And let's look at 3 times itself 0 times. It's a strange thing to say. Because you say, what does 3 times itself 0 times mean? Well, if we follow the trend of dividing by 3 to move ourselves one block to the left on our sort of chart of exponents, 3 raised to the exponent 0 has to be 3 divided by 3. 1. Let's take it even further. Divide by 3 again. That's going to be now, watch the exponents from the 3 times itself 4 times, times itself 3 times itself 2 times itself 1, times itself 0, 3 times itself minus 1 time. Continue the trend, 3 times itself minus 2 times, 3 times itself minus 3 times. How do you continue moving off to the left? Well, just as we always have, you divide by 3. So take 1 and divide it by 3. What do you get? A third. Divide by 3 again. What do you get? A ninth. Divide by 3 again. You get a 27th. But a few things result from this when you start thinking about it. So note, no matter what the value would be, that would be down here where the 3 is. Note, if we had something like 4 to the first, 4 to the second, 4 to the 0, 4 times itself 1 time is 4. How do you get back to 4 to the 0? You divide by 4. 4 divided by 4 is 1. 5 to the 0, 5 to the 1, 5 squared. 5 times itself 1 times is 5. To get back one spot, you have to divide by 5. 5 divided by 5 is 1. What if it was 6 to the 0 and 6 to the 1? 6 to the 1 is 6. To go back one space to 6 to the 0, you'd have to divide by 6. But 6 divided by 6 is 1. So, in fact, x to the 0 power is 1. And just to be fully make sense of this, x to the 0 power is 1, so long as x is not 0. Because, well, to be clear, if x was 0, the statement wouldn't sort of make sense, right? Because 0 to the first power would be 0, divided by 0, you'd sort of be back at 0. So in order for this thing to make sense, we have to deal with something non-zero. But no matter what non-zero thing we had, if we had one copy of it, we'd have that non-zero thing. And to go back one spot to find out what that non-zero thing would be raised to the 0 power, we have to take that non-zero thing and divide it by itself. But any non-zero thing divided by itself is 1. So x to the 0 is 1, no matter what non-zero thing x is. Another observation. Take a look at the numbers that show up in this chart. On the one side of 1, you have 3 and 9 and 27 and 81. And on the other side of the chart, you have 1 over 3 and 1 over 9 and 1 over 27. And hell, if you took it one step further, you have 1 over 81. So you can see the same numbers that show up in the numerator on the right are the numbers that show up in the numerator on the left. The same numbers that show up in the numerator with the positive exponents are the numbers that show up in the denominator with the negative exponents. So we can say the following. Any number which is raised to some negative exponent, let's just say n is whatever the negative exponent is. I tell you what, we used n for the radicals. Let's not use n here, let's use a, just to use something different. If you're taking x and you have now divided it away a times, right? Because we took 3 in this case and divided it away a certain number of times. You got a third, the 9th, and the 27th, and so on. Take x and divide it away a times. That's like 1 over x multiplied by itself a times. Because if you take x and multiply it by itself a times in the denominator, it's like taking x and dividing it away a times. Because just like exponentiation is repeated multiplication, and positive exponents then mean multiplication repeatedly, well, negative exponents are going to mean the opposite of multiplication repeatedly, namely division repeatedly. So x times its, well, sort of x raised to the minus a power is 1 over x to the a power. The negative exponent has the same number as the positive exponent, just showing up in the denominator. And that's all this is saying. Anytime you have a negative exponent, It's that positive exponent showing up in the denominator, because anytime you're doing repeated division, that's like multiplication in the denominator. All right, with this in mind, we can actually derive a few additional facts that can be of interest and of use to us. So let us try to find the following. Let's try to find x to the a times x to the b. I claim with our knowledge of exponents to this point, we can figure out what this is. Because what is x to the a times x to the b? Well, x to the a is just x times itself, a total of a times, and x to the b is just x times itself, a total of b times. So when you have x to the a times x to the b, you have x multiplied by itself a times and then b times. In total, how many times would x be multiplied by itself? Well, say a was 3 and b was 5. You'd have 3 x's here, 5 x's there, that's a total of 8 x's being multiplied. What if a was 10 and b was 2? You'd have 10 x's here and 2 x's there, that'd be 12 x's being multiplied. No matter what the size of a and what the size of b, if x is being multiplied a times, then x is being multiplied b times, that is a plus b x's being multiplied. So in other words, whenever you have two terms that are exponents being multiplied, you can simply add the exponents. A copies of x multiplied, b copies of x multiplied. In total, that's a plus b copies of x. So another way to write that is just to say that's a plus b times that x is being multiplied. Another statement to find. What about x to the a raised to the b power? So now we have an exponent raised to an exponent. How do we make sense of this? Well, let's think about what this means. X to the a raised to the b power is what? First, let's deal with the x to the a. That is simply x times itself, a times. But now this is being raised to the b power. And when you take anything and raise it to the b power, what do? Well, you have to repeatedly multiply b times. So what we're going to do is take x times itself, a times, and we're going to multiply it by itself, b times. Well, how many x's are there? There's an a's worth of x's in the first parenthesis, and an a's worth of x's in the second parenthesis, and an a's worth of x's in the next, down here to the a's worth of x's in the b parenthesis. How many a's are there total? Total number of, or excuse me, how many x's are there total? There's a in the first parenthesis, there's a in the second parenthesis, there's a out in the b parenthesis. But if you take something added and repeat it multiple times, repeated addition is just multiplication. So a plus a plus a plus a, b times, is just a times b. So x raised to the a raised to the b power is just x to the ab power. Because we have x written out a times, b times over. In total, that's ab x's written, all being multiplied. X raised to the ab. Another fact that follows very naturally from the facts that we've seen here. A to the m over a to the n. Oops, let's use a and, excuse me. X to the a, x to the b. Now here, instead of the terms with exponents being multiplied as they were previously, we have terms with exponents being divided. How are we going to deal with this? Well, the thing to think about is what we saw previously. When you have a certain number of things being multiplied in the denominator, that's like that thing being divided. So since x is being multiplied b times in the denominator, That's like x being divided away b times. So anytime we have a certain thing being multiplied in the denominator, it's like that certain thing being divided. So x to the a upstairs is just x to the a, but x to the b being downstairs is now x to the minus b. Can we simplify this more so fully? Well, yeah, right? Because when you have x to the a times x to the b, just like we saw before, you just add the numbers together. So x to the a times x to the b added together is x to the a minus b. What can we get from this? Well, note, two exponents multiplied, you add the exponents. Two exponents divided, you subtract. And that makes sense, right? Because multiplication of exponents corresponds to addition, division of exponents corresponds to subtraction. Multiplication, addition, division, subtraction. It makes perfect sense in terms of the operation, multiplication, and its inverse operation, division, the operation, addition, and its inverse operation, subtraction. Now, what can we actually do with this? Let's put this practice, let's put these facts into practice. Let's run through a couple examples to sort of familiarize ourselves with the process. So what if we had y to the fourth times y to the minus 7? This is a very simple problem. All we have is exponents being multiplied. When exponents are being multiplied, we simply add them together. So we add 4 and minus 7, we get minus 3. What if we had 3x raised to the fourth power? Now here we have to make sense of what this means. This means 3x times itself a total of 4 times. But what is that? Well, 3 is going to be multiplied by 3, is going to be multiplied by 3, is going to be multiplied by 3 to give you 81, and x is going to be multiplied by x, is going to be multiplied by x, is going to be multiplied by x to give you x to the fourth. Another. C to the ninth over c to the fifth. How do we deal with this? We deal with this just like we dealt with the example above. When you have c times itself in the denominator 5 times, that's like c divided by itself 5 times. How do we deal with this now? We've taken what was in the denominator as a power and written it as a power that's negative because of, well, as mentioned already, multiplied by something a certain number of times in the denominator, that's like dividing by that something. But now we just have exponents being multiplied. When the exponents are being multiplied, c to the 9, c to the minus 5, you just add the exponents 4, c to the 4 specifically. Two more here to round out our exponent examples, and then we'll tie the radicals and exponents together. So let's do y squared x over z to the fifth, and this is all raised to the fourth power. Now think about what's going to happen here. You're going to take this thing times itself a total of 4 times. Just like we did before with the 3x. Now I claim, when you look at this thing 3x to the fourth, or y squared x over z to the fifth to the fourth, you're really just applying this property. Because you're taking the 3 and multiplying it by itself 4 times. You're taking the x and multiplying it by itself 4 times. Here, you're taking y squared and multiplying it by itself 4 times. Well, what do you get when you take y squared times itself 4 times? That's a total of y to the 8th. 2 times 4. What about the x times itself 4 times? That's like x to the 1 times itself 4 times, right? Because x, a single copy, is just x times itself once. And x to the 1 raised now to the fourth power is 1 times 4, x to the fourth. What about downstairs? We have z to the fifth times itself 4 times. So if z to the fifth is being repeated 4 times, that's z to the fifth, z to the fifth, z to the fifth, z to the fifth. That's a total of z to the 20. 5 times 4. And that's all in the denominator because this z to the fifth being divided away is all in the denominator. So the result, y to the 8th, x to the 4th, z to the 20th. y squared 4 times over, y to the 8th, x 4 times over, x to the 4th, z to the 5th 4 times over, z to the 20th. What about this guy down here? Y over 3z squared raised to the negative 2. This is a particularly interesting example because it's not just something raised to a power raised to a power, but it's a power raised to a negative power. Now you got to think, how did we deal with negative powers? Well, negative powers could be put in the denominator as positive powers. Or, thought another way, negative powers could be brought to the other side of the fraction bar as positive powers. So anytime you would be dealing with this thing to the minus 2 power, anything to the negative power, anything to the negative power is just taking what's upstairs downstairs and taking what's downstairs upstairs and making them positive. Negative power brought downstairs becomes positive. So, what do we got here? To deal with this negative exponent, we can take what's upstairs downstairs, take what's downstairs upstairs, and now, instead of this being negative, it's now going to be a positive exponent. To complete the multiplication, we just have 3 times itself twice, that's 9, z squared times itself twice, that's z to the 4th, 2 times 2, and y times itself twice, y squared. But the long story short is, negative exponents can exist on the other side of the fraction bar as a positive exponent. We saw in general that x to the minus a is 1 over x to the a. A negative exponent upstairs becomes positive downstairs and vice versa. So to take the negative exponent and make it positive, you just take what's upstairs downstairs, what's downstairs upstairs. Okay. Now at the beginning of class, I claimed that radicals and exponents, these two seemingly distinct things, are actually very related. Let's remind ourselves what radicals are. So if we're talking about the 4th root of, let's say, 81, which we know to be 3, what is this? This is the number that when multiplied by itself 4 times is 81. Right? The 4th root of 81 is the number that when multiplied by itself 4 times is 81. Let me rewrite this. Instead of in terms of 81, let me just write this in terms of x. To say any 4th root is just a number which times itself 4 times is what's inside. I mean, hell, the 4th root of 81 is what times itself 4 times is 81. The 4th root of x is what times itself 4 times is x. But now, I claim that there is a power we could put on our x equal in each case. Because note, above, we have the 4th root of x 4 times over. Every time we're dealing with the 4th root of x, each of these 4 things being multiplied is exactly the same. I claim that each of these 4 things being multiplied could be exactly the same to get x. What is x in terms of exponents? Well, just like we saw here, and just like we've seen a couple times in fact, like 3 to the 1 is 3, 5 to the 1 is 5, 6 to the 1 is 6. X to the 1 is x. So when you just have a number written once, that's itself multiplied by itself once. What could we put in the question marks here to be the same number in each case to where the exponents will multiply and be 1? Remember, when we multiply exponents, we just add them. So I need a number here which adds to itself 4 times to be 1. What number adds to itself 4 times to be 1? It's got to be exactly a 4th, right? Because a fourth plus a fourth plus a fourth plus a fourth is 4/4, which is 1. But what does this tell you? Above, we see the number which multiplied by itself 4 times to be x is the 4th root of x. And below, we see the number that would multiply by itself 4 times to be x is x to the 1/4. But that tells you then that those two things are representing the exact same number. So, in other words, in conclusion, the 4th root of x is just x to the 1/4. But think about this. The fact that we dealt with the 4th root in that case is not really special in any way. We could have dealt with the 5th root of x and used x to the 5th, or the 6th root of x and been x to the 6th. Because the 6th root of x would have to multiply by itself 6 times to be x, and the exponent we need would be a 6th to add to itself 6 times to be 1. Hell, square root 2 would be a half. In general, the nth root of x is just x to the 1/n. We've taken what we saw with radicals and we now have harmonized it with what we've seen with exponents. I wish we could get into more detail on this in terms of timing and everything, but we simply just don't have enough time for today. So I'm going to pick back up here next time, Wednesday, when we meet together, and we're going to see more examples sort of putting this into practice. But the long story short is, radicals and exponents can be translated from one to the other if you sort of use this fact to pull it off. And again, we'll see more examples when we go through this next time. Again, I thank you for your attention, especially considering the fact that our first 3 times of class meeting together have been via video. I wish you guys a great weekend, and ultimately, a great extended weekend. I'll catch you guys on Wednesday in class here, HSS, and we'll just pick off from there.